we are asked to find the Thévenin equivalent circuit for this network. That means that we're going to want to find the open circuit voltage. That'll be our Thévenin voltage, and then after we have that, we can consider our options to find the Thévenin resistance. Since we're finding a voltage, it seems logical to use nodal analysis. We can go ahead and put the ground down at the bottom. If this is all 0 and we have a 24 volt source, then this whole node that we have up here is all going to be at 24 volts as well. We have another node on the other side. Again, this is one single node, and we can assign a variable to it, but we've already done that. We've said that this is the open circuit voltage, is the voltage between ground and this node, so in fact it seems that VOC, our open circuit voltage, is the voltage at this node. We also want to consider our currents. We have currents flowing out, IX, and the currents from the sources, and then let's say that we have a current flowing this way. We'll call this I1. If we want to solve for the open circuit voltage, we will write a KCL equation. We consider the currents entering and leaving this unknown node here. The way we defined our currents, all of them are flowing out, so they're all positive, all on the same side of the equation. We've written everything in terms of IX or I1 or the independent current source. But we're interested in VOC, and we want to compare this voltage to IX. And so in this case, VOC, the open circuit voltage, is the voltage applied across that 8 ohm resistor, and so we can go ahead and identify that IX is thus. We can also combine these terms here. We have 3 IXs, and we have another IX. So in fact, we have 4 IXs total. Then we can simplify. We can substitute in for IX this equation in terms of VOC. We also want to represent I1 in terms of VOC. And we find that VOC is 8 volts. Next, we want to find the Thévenin resistance. Because we have a dependent source, we can't deactivate all the sources, but what we can do is deactivate the independent sources, and we can apply a test voltage and measure what the test current is and use that to find the Thévenin resistance. So we'll start there by redrawing the circuit. Here we've redrawn the circuit, but we want to deactivate our independent sources. So here I have an independent voltage source. To deactivate a voltage source, I want there to be 0 voltage, which means I need to have a straight line, just a wire. I also want to deactivate this current source. To deactivate a current source, I want there to be 0 current, and so I will leave an open circuit. I can't deactivate the dependent source. That is fixed there, so what I'm going to do is apply a test source and measure the resistance that way. In this case, I'm looking for a Thévenin equivalent circuit, so that means that I'm going to use a test voltage to match the voltage source in a Thévenin circuit. So I have a test voltage that I'm applying, and I'm going to be measuring the test current that's flowing through the circuit as a result, and that shows us what the effective resistance is here. In this case, I have current flowing in that I'm trying to find, and so I can go ahead and use KCL. Effectively, I'm doing a nodal analysis again, because what we have here is one big node. Again, if we ground the bottom, then we have the test voltage is this whole node. Some of the current flows this way, some of the current flows that way, and then we'll have some current flowing out on this side. Again, we'll call this I1. And so we see that any of the test current flowing in, some goes this way, some will go that way, some will go that way. And we can say that the test current flowing in is going to equal IX flowing out and I1 flowing out, and 3ix flowing out. But we're interested in the test current and the test voltage, so we want to represent Ix and I1 in terms of these quantities. Well, Ix is flowing from this node to ground, so Ix is going to be Vt minus 0 over 8. I1 is flowing from this node, which is Vt as well, to this node, which is 0, and so I1 is going to be Vt minus 0 over 2. And then we have the dependent source, which depends on Ix, and we already have an expression for Ix in terms of Vt. We can simplify this if we have 1/8 of Vt and 3/8 of Vt. That is a half of a Vt. A half of a Vt and another half of a Vt is going to give us 1 whole Vt. If It equals Vt, we want to solve for the Thévenin resistance, which is voltage divided by current is resistance, and Vt over Vt is 1. So our Thévenin resistance in this case is 1 ohm. We were asked to find the Thévenin equivalent circuit. We found the open circuit voltage, which is our Thévenin voltage. We used a test voltage source to find the Thévenin resistance. Our Thévenin equivalent circuit is then a voltage source in series with a resistor with 8 volts for our source and 1 ohm for our resistance.